Okay, hi everyone. Well, I will talk a little bit about some optimizations we've been doing at Caesar Systems in the process of bytecode generation. But first of all, I'd like to point out that even though we had in mind some optimizations, our main goal was not to implement these optimizations, but to get a deeper understanding of the bytecode generation process in particular, and the compilation process in general. So, well, the best way we know for exploring some domain and documenting the knowledge we obtained from that exploration is Smalltalk, so well, we did it in Smalltalk, Smalltalk. So, having that in mind, let's take a big picture of the three different levels of languages we are dealing with. In the first place, we have, of course, Smalltalk code. And then we translate this code into bytecodes, and finally we translate bytecodes into machine native code. So for instance, we have here a simple method in which we have some variable, temporary variable, and then we use it as an argument, of a message. Well, these are the bytecodes corresponding to the method. We have here the list of bytecodes, the signal in the first two bytecodes, and then the message send. So, well, this is actually translated or, yes, nativized by the just-in-time compiler to native code. Here we can see the association between bytecodes and native code assembly. So regarding the architecture, the VM architecture in which we've been working on, just a couple of words. It is based on Digitox VM, but it basically follows the model proposed by Alan Wirthbrock in this paper, except for some differences. But essentially, this VM specifies several special purpose registers plus stock, which in this case is the same native stock. And as I said before, it comes with a jitter, or just-in-time compiler. So this is just a picture of a message send with the correspondences between registers and the stock and the variables of the method. For instance, we have one register for the receiver of a message, and well, arguments are all passed using the stock. Here, there's one difference between the model proposed by Alan Wirthbrock, and that's the last. In this implementation, all the arguments are passed on the stack, and except for some special cases in which the register R8 is used for binary message sends. But this is a big picture. I'm not going into detail. Well, speaking specifically about optimization, the first question is why, and of course there are obvious reasons, for instance performance issues like reducing processor cycles and unnecessary memory accesses, but also for simplicity purposes. At this point, we can assume that if we reduce the complexity at the level of bytecodes, the process of nativization will take or will be affected by these optimizations in a positive way. So we can assume, we can think, we can expect that reducing bytecodes complexity will reduce native machine code complexity. Well, as I said at the beginning, our main goal was to end up with a framework in which not only the optimizations we had in mind, but also new optimizations can be implemented and tested. And accessibility is another reason, because since this is entirely written in Smalltalk, we can share this with another Smalltalkers and make the compilation domain accessible to any of them, and not only for specialists. That's the purpose. Make this accessible to Smalltalkers and not specialists. I feel this. This is the same guy, but
we know.
That's a feeling. Okay, how? Regarding about how to make all this work. Here is a picture of the process of compilation. Main stages. We start from source code of a method with several sentences. Then this code is parsed and an AST is built. And then from this AST, the previous approach generated bytecodes in terms of bytes. Not bytecodes as objects, but directly a byte array. So the idea is, of course, to insert some process in the middle of the last translation and generate bytecodes, then optimize those bytecodes, and finally translate those bytecodes into actual bytes. It's just encoding phase. Well, but most important is what to optimize. Well, here are three cases that we find interesting to optimize. The original ideas come from these cases. The first of them is related to loading bytecodes. Loading bytecodes are some subset of bytecodes that are used to load objects into registers. In our case, register R. For instance, suppose we have this simple method in which we have again a temporary variable t, and we assign some number, and then we send a message to it. These are the bytecodes corresponding to the previous code. So if we take a look at the second bytecode, which stores the object points the object 10 by the temporary t, or stores the number 10 into temporary t, we can be sure that t will be in R, because that's the mission or the meaning of a stored temporary bytecode. store what it is in the register R. So the third bytecode can be removed because we already have the the variable t in register R. So that's actually what we do. We remove this, and we can assume at this point that this will at least reduce in one the number of native code. So, but in order to proceed with these optimizations, we have to take some care because, as you may know, we have bytecodes for controlling the execution flow. So we can have several execution flows. And the analysis that we have to do consists in, given this situation in which we have a candidate of a low temporary bytecode to be removed, that is a load-in which is preceded by a store temporary of the same variable, analyze every possible execution flow. Execution flow is controlled by jumps, so we have to analyze the entire list of bytecodes and see if in every possible execution flow the variable t is in R before jumping. If that's the case, I mean, if after the bytecodes preceding the jumps, variable t is in R, we can proceed in removing this bytecode. Another case, is related to push bytecodes. Suppose we have again one simple method like this in which we use t as an argument for a message. So bytecodes corresponding to that method are these. In this case, our bytecode that pushes the argument is separated by one bytecode, which is the loading of the receiver. So we cannot directly remove or change, not remove. We have to push the argument. But if we think about the send semantics, from Smalltalk point of view, we must guarantee that we follow these steps in order. That is, evaluate the receiver and load the receiver in some register, then evaluate the arguments and push them onto the stack, and finally send the message. But from the bytecode's point of view, we have some freedom under some special and certain cases. We can swap between the first and the second step. So we can push the arguments before loading the receiver. Okay? So that's what we do. If we are under those conditions, we can switch between those bytecodes, and then we will obtain the following situation. The push temporary t will be right after store temporary t. So in this case, what we can do is, knowing that variable t is already in R, we can directly push the register. This is, I don't know, it's just an assumption at this point, because we can assume that this would correspond to some push memory direction, while the push register will correspond to a push register. So this is an assumption, but making that assumption, we can proceed with this optimization and change the original push temporary by a push R, which we can assume that is push some register. So again, in order to proceed with this optimization, we have to analyze every possible execution flows and see if variable t is already in R. Here I am talking about temporary variable t, but this applies for every kind of variable, push, instance variable, temporary, whatever. I mean the push and the load cases. Well, finally, jumps. Jumps, as I said before, are bytecodes that are used for controlling the execution flow. So, for instance, suppose we have this method here, and as you may know, messages like on and if true can be inlined, and in fact they are inlined. That is, they are translated to jumps. So these are the bytecodes corresponding to the previous method, and here it is pretty much obvious that jumping, in the case, we have one conditional jump in the second place, but let's suppose false is in R, so that we actually jump, reaching that point. Instead of jumping from 2 to 6 and then to 11, which we can directly jump to 11. That's the obvious optimization. And that's what we can do. But again, we have to take care of every possible execution flow because, well, here we have a simple example in which we have two chains of jumps. At the left, we have one conditional jump followed by one unconditional one, and so on. And finally, we end up here. Well, in that case, if false is in R, we will jump, and we will jump until we reach this bytecode, so we can jump directly as in the previous case. But at the right, we have another example, another chain, that in this case, we have a combination of two conditional jumps, but of different conditions. So in this case, we can, yes, we can optimize this chain, but since we are jumping if the register R contains true, we can directly jump to the following bytecode. So the chain at the right will be optimized in this way. Okay? Well, that's all about what until now. Well, this is a picture of the compilation process and the main objects involved in it. As I said before, we start from source code, and then the main guy in charge in this implementation is the smalltalk compiler, which cooperates with some other guys like smalltalk parser. This obviously parses the code and translate sentences into AST nodes. Once we have the AST, the following phase of the process is in charge of a new guy, which is the bytecode in parse3 visitor. This guy is the one corresponding to the instantiation of bytecodes. Instead of just encoding that AST, here we instantiate bytecodes. So this object cooperates with three objects. The bytecode generator, which actually creates bytecodes, and the bytecode optimizer. The thing is that some optimizations should be done during the bytecode emission. I mean, it's pretty much convenient to perform those optimizations during the bytecode emission. So here, the bytecode generator will interact with the bytecode optimizer each time it creates a new bytecode. But we decided to remove from the bytecode optimization the logic of analyzing, for instance, the execution flows and so on. So we decoupled the logic of analyzing, and we created this bytecode. This bytecode is the bytecode analyzer. This is central in this implementation, and this guy will say, for instance, is at a given bytecode, some variable is in some register, for instance, register R. So, provided that information, bytecode optimization can proceed by changing bytecodes, one bytecode to another, dropping bytecodes, and so on. So once we have a list of optimized bytecodes, we can proceed with the compilation process. So we only have to encode these bytecodes into actual bytes to generate a compile method. So we created a guide, which is the encoded bytecode, and we used a visitor pattern for implementing it. So this traverses, or I don't know, takes every single bytecode and encodes. Well, finally we get the bytecodes or the bytes corresponding to the code, and we can build our compile method. So the main objects, or a picture of all the objects of this framework, we have verified a complete hierarchy of bytecodes. So we have a smalltalk bytecode, and we also created a bytecode parser using petit parser. This is necessary for making the opposite translation from bytes to bytecodes, and it is used for having a compile method, printing its bytecodes, or even making all the queries, all the reflection queries we are used to make on compile methods, such as from a set of compile methods, which of them access some, let's say, this instance variable. We can now talk directly to bytecodes instead of parsing for those queries. So we have the bytecode generator, we have general or abstract bytecode visitor, which has printing bytecode visitor subclass for printing purposes, and the encoded bytecode visitor. And we have a bytecode optimizer. Of course, we have a particular optimizer for particular optimizations, load optimizer, push optimizer, jump optimizer, and so on. And the bytecode analyzer, I explained that before, and we have implemented two more objects for analyzing our optimizations. One of these is this simple object that, given a bytecode optimizer and given a set of methods, will just say which of them and in which degree they are optimized. So, useful object. And this is the other object. This is an object for running benchmarks on our optimizations. And this is pretty much simple also. Given an optimizer and given a compile method, it will, given a source code, well, it will compile the method without the optimization, with the optimization disabled several times, and then it will evaluate the method. That is, send a message to some object. And after that, we will do the same, but this time with the bytecode optimizer enabled. So finally, it will provide some statistics about this optimization in this particular method. Okay? Well, this guy also has several services for reporting purposes, such as graphics or charts. And let's see in a few minutes the results we obtain. Regarding the load optimization, the first optimization, we from an image of roughly 110,000 methods, almost 17% of them are optimizable, and the most optimizable method, that is the method which contains more loads that can be removed, has 19 loads. Well, the first approach we took here was to draw the results in a histogram of the average time. So in green we see we took 1,000 averages of 100,000 repetitions. And the green curve corresponds to the optimized version, and the red one corresponds to the non-optimized. And this is the average time. So our first expectation was to see the green curve more shift or to the left. That wasn't the case. So we applied, thanks to Javi, some statistical tool which is known as bootstrapped. This tool basically, given some sample, statistical sample, resamples that sample and provides information about the behavior of some statistical indicator. So we are here interested in average time. So we did this analysis, and what we can see here is the behavior of the average time, the mean average time. The mean of the average time corresponding to the optimized version is the green curve, and here we can see that the mean average time is to the left. So this optimization actually optimizes something. Well, the same analysis for pushes, the same image, almost 9%. The most optimizable method has 11 bytecodes, or 11 push bytecodes. Here the difference is less obvious or less visible. So again, we use this magical tool, but we obtain now that we have obtained that the optimized version is a little bit faster than the in terms of the mean time, of course, mean average time. Regarding the push optimization, we have the same image, less percent of optimizable methods, but here we have in the first histogram a difference in the time. So for completeness, we make the second analysis, and here the optimization is obvious. So to conclude, as I said at the beginning, we think that instead of implementing optimizations and, I don't know, hacking some stuff, we prefer building a framework for sharing our knowledge and trying new optimizations. So that's it. Questions? We generate the bytecodes, and in this particular image, the backend information pushed into the compile method doesn't be. It is not affected, but that.
The divider follows bytecodes, right? So if you modify the bytecodes, the divider will follow the bytecodes.
Yeah, but normally when you copy it, the selection code jumps this way, like reading. I mean, does it, after optimization, does it jump like randomly, or do you understand my question, or?
Oh yes, I understand your concern, but it doesn't happen. There is one optimization that would change the divider, because that's he didn't implement because of that, which is sometimes you don't need to store the value of the result of an expression into a temporary, to use then the temporary as, say, an argument or receiver. But if you skip that, then it will be nil.
Yeah.
So,
One thing.
And the chance to bytecodes.
Another optimization you could make sometimes declare packs which are not used at all, but you still push stuff on the stack. It's very simple.
yes.
Yes.
Hola.
Hola. Well, thank you.